This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
So let me start a little bit talking about the first project then. And what I had in mind you would demonstrate to Suhail. So again, it should be very simple. And be prepared to demonstrate the following. I think there are 4 parts, right, to this first assignment. And the first part, if I remember this correctly, was just about showing this geometrical construction of the de Castelnau algorithm. So what the user should be doing, what you demonstrate to Suhail, is something like this. So click a point, click a point, click a point, click a point, and then you will connect these points. And then you show somehow this baseline or the parameter line from 0 to 1, and you will show a particular value or location on this line, and you show all these intermediate points and polygons coming out of this geometrical construction. And here's a point on the curve. You show something like that. Okay? And then it would be cool, of course, if you were to show this construction in the context of the entire curve. So as a background, you also could show the curve, which is rendered using 1,000 points or so. And then it would be really super cool if the user was able to move this little evaluation point around, and when this point or this evaluation location is moved around, this whole configuration changes, right? So if when I move this evaluation point to the left, then the configuration would move to the left. So something like that. Next part was, I guess, to compare the evaluation scheme. And so one scheme for this particular curve, you would start with the 4 original control points, and then you use this double loop to evaluate from 4 points to 3 points, from 3 points to 2 points, and from 2 points to 1 point, right? And that was encoded in a double loop. And you do some timing, how long that takes for 4 control points, 5, 10, 15. And then the other way to get this point is a curve point at parameter t, right, the last entry there. And the other way to do it is to evaluate the sum directly, I from 0 to n of the control points that you click, and then bi n of some value t. And then you have to have another function that returns the value of this Bernstein polynomial. And the tricky part there is that you have to deal with this n factorial over some other factorial stuff. And you will sooner or later run into some kind of integer problems, okay? And when you click more than 50, 60 points, you will see that you hit a limit there with respect to integer, okay? So that's the reason why I want you to play with that. But again, you should just say, if I compute the point here, it will take 1.4 milliseconds. And if I do it this way, it takes 2.8 milliseconds. Okay, so just do some timing there. Part D was related to a subdivision. So again, the user would just click a bunch of points, defining a polygon. And then here you have the parameter line. And the user would also click a particular point where to subdivide. And you would just subdivide at this location. So again, the routine would be just to do this, to evaluate for the location of this marker. You get the intermediate control polygons. And then you would say, okay, the control points for the left curve are these guys, circles. And the control points for the right curve are these points. And you have a left segment and a right segment. So somehow you want to show that you generated these new circles and these new squares, right, from the original ones. And the last one had to do with subdivision. So I just show it for 2 line segments, but I would like to see when 2 lines are crossing. So a user would click specify a control polygon of a first curve, just a line in this case, and the control polygon for a second curve, another line segment. And then all you do is these bounding box tests, right, where bounding boxes intersect. And ultimately what I would like to see that I have 2 bounding boxes here in this region that do overlap, and they are very small. So in the end, I would like to see very small overlapping bounding boxes that indicate where my eye sees the region, the location of an intersection point. Okay, and you do that also for higher order curves. And then again, if these are quadratic curves, I would like to see two boxes in that region, in the general region or neighborhood of that point to overlap. Something like that. Okay. However you will demonstrate or show this to Sahil doesn't matter so much as long as you can convince Sahil that your program can do these things. Okay. The interface, the graphics doesn't have to be super cool. Sahil just has to be assured that your mathematical functions work. Okay. Sounds good? Are there any questions to the assignment still? Or no? Was it too difficult or too easy or just fine? Level was fine? Also the time for it was enough? Or? Okay. You started the night before? Or? Yeah? So if you can do it in one night, then it's definitely not too difficult. Okay, so degree elevation and degree reduction is the topic for today that I want to talk about a little bit more. Again, someone remind me what this idea of degree elevation was. What was it? Degree elevation. Help me.
Take a curve and control points. And make an equivalent curve to use the +1 control points.
Is he right? So we start with a control polygon that has n+1 points. And then we want to represent the same curve using a control polygon consisting of n+2 points. Right? That was the idea. So going from a degree n representation to a degree n+1 representation. But the curve is the same. So that was the topic of degree elevation. So let's just go over that briefly again. That was from last time, degree elevation. Basic principle was you go from, say, n equals 2 to a representation n+1 equals 3. So geometrically, I start with a polygon like this, and I call the points B0, B1, B2. And I would like to get 4 control points instead of using those 3. And there was one governing formula, the important formula. The formula that we use to compute the new control points, which are these. I just sketch them. I call these control points B0 bar, B1 bar, B2 bar, and the last one, B3 bar. So the BI bar points are related to the original BI points according to this rule. And the rule says that this BI bar point, the new point, relates to BI minus 1 plus some fraction of BI. And then the ratios in front were divide by n+1, divide by n+1. And here it was I times, and here it was n+1 minus I times BI. So that's a very important formula. We don't need to remember that. And I runs from 0 to n plus 1. So the triangle control points define another control polygon, namely this one. But the curve implied by both polygons is the same. So there is only one curve, C of t. And the only thing that we have to remember is the geometrical construction for this. Geometrical construction is explained easily by 2 examples. And the 2 examples allow you to see it for the general case. Okay? Only need to remember what this means geometrically. What this means geometrically. And I put this on the next board. So from n equals 2, we go to n plus 1 equals 3. And I will do one other example where we go from n equals 3 to n plus 1 equal 4. Okay, so we start with 3 control points. And the new ones are coinciding with the ones at the end, right? And then the middle guy gets replaced by 2 new ones. And those come from certain ratios on these line segments, okay? And these ratios are 2 to 1 and 1 to 2. Only need to remember these ratios. Where do these ratios come from? Look at this number, n plus 1 equals 3. You only have to think about ways to decompose 3 into 2 numbers that you add, giving 3. 2 plus 1, 1 plus 2. So those are the ratios, and that's the way you get the points. So these are the old points, Bezier points, and the triangles are the new Bezier points. Bezier points. Now the other example, the number we have to represent as a sum is the number 4. So we start with a polygon that looks like that. It has 4 circles as control points. And so where are the new control points? Well, they go inside with the control points at the end. And now I put certain ratios on this line segment, and these ratios are given by the different ways I can write the number 4 as a sum. I can write it as 3 plus 1, 2 plus 2, 1 plus 3. And so those ratios will get mapped here. So the first ratio is, as I said, 3 to 1. The next ratio will be 2 to 2. And the last ratio will be 1 to 3. So the new polygon then is this one. And here the new polygon is this. And there's always just one curve. Okay, and then from here you see the general principle, how that would continue, right, for higher numbers. So it's clear? Does it make sense? Okay. So far, so good. Now, there's the other word on the board, reduction. Degree elevation and degree reduction. If I can elevate something, I can also reduce something, right? What would that mean? Elevation, reduction, they are opposite processes, right? It's the same thing, but looking at the process in the other way, right? I start with many points, and I want to reduce the number of points. Here I started with n plus 1 points, and I go to n plus 2. Now I wanted to do it the other way. I want to start with n plus 2 points and go down to n plus 1. Is that possible? Pardon?
Doesn't seem like the case.
Here, for the degree elevation, it was always possible to represent this given curve with a polygon that has 1 point more. Okay, so adding an addition or using a representation that is of 1 degree higher doesn't change the curve at all. I just use 1 more control point. That's it. So I can do that exactly. So now I want to go the other way around. I start with control points. I want to take 1 away, in a sense. Can I do that? Can I do that? So let's go to our idea side and convince ourselves that I cannot do that. Okay. So now we go to degree reduction. Degree reduction. Okay. Let me start with a cubic curve. So a polygon like that. Okay, so the curve, when you draw it, would look somewhat like this. Okay, right? You believe me? And now I say, instead of using 4 control points, I would like to use 3 control points. Can I do that? 3 control points, the curves with 3 control points always look like this, right? They're always convex curves. If I have only 3 control points, the curve is always convex. This is a convex curve. No, this curve has an unhappy inflection point there, right? Okay, if I have an unhappy inflection point, then I can never represent it with just 3 control points. So if I cannot get it exactly, then what can I try to do? Get a good estimate, a good approximation for it, okay? So I cannot represent this with a parabola or quadratic polynomial exactly. So maybe I use something like this. Okay, and then the curve I get is this. And maybe I call that good. That's the best I can do. Maybe I cannot do better. Okay, so the important point is you cannot go from n plus 1 to n without introducing error, without introducing error. Which is too bad, but such is life. In the end, I will come back to the geometry. In the end, we only have to understand the geometry. But before I put the geometry on the board, I have to motivate it with the mathematics, right? So the governing formula we already had on the board. It was the same formula, but we solve it for the other things on the right-hand side. Huh? So what was given before is now the unknown. All right, so now we talk 2-degree reduction. So we have a curve given. Given is now a curve of this form, C of t equals sum I from 0 to n plus 1. Okay, it has n plus 2 control points. bi n plus 1 of t. And I would like to represent it with 1 control point less. Goal or construct. We want to construct a new curve, and now this curve is really a C tilde. It's really different. It's not no longer the same curve, which is sum I from 0 to n, some other control points, bi bar, bi n of t. Okay. So the formula that describes this relationship we had on the board before, except in the previous formula. On the previous formula, we called these guys the bars, and these didn't have the bar. It was reversed. So it's the same formula, except where we had the bar before, we take it away, and where the bi's didn't have the bar, we put the bar on. So we just reverse that. So the formula in the structure is the same. So we have now bi, right, equals, there were certain ratios there, times bi minus 1 bar plus some fraction of bi bar, and then we divide it by n plus 1. And here we had I, and here we had n plus 1 minus I. Okay. But now we have to solve for the bi minus 1 bar and the bi bar. How do we do that? Okay, but unknowns, but the unknowns are these guys. The unknowns are bi minus 1 bar and bi bar. Okay, so we have to solve for those. So what do I do? Well, first I multiply both sides by n plus 1, right, to get rid of that. So I just say times n plus 1. When I do that, what happens? Then I get the formula n plus 1 times bi equals I times bi minus 1 bar plus n plus 1 minus I times bi bar. Okay. And now I need to solve for this guy and I need to solve for that guy. So I get two different equations. How do I resolve that misery? So in the first attempt, I will solve for bi bar. So there are two equations, two new equations. And equation number 1, solving this for bi bar. So I have bi bar equals, I divide by something, and that is bi, and then it's minus times bi minus 1 bar. Okay, I have to divide by n plus 1 minus I. And the bi has n plus 1 in the numerator, and the bi minus 1 bar has I in the numerator. Second equation I obtain by solving the equation for bi minus 1 bar. So that is bi minus 1 bar is something minus something. And what is it? Bi minus 1 bar, again, that is bi here. And then it is minus bi bar. Okay, so what do we divide by? Bi minus 1 bar, we divide by I. And in front of bi, we have n plus 1. And in front of bi bar, we have n plus 1 minus I. So we have two governing equations all of a sudden. And here we have to say I runs from where to where. I runs from 0 up to n. And here, I has to run backwards. I runs from n plus 1 backwards to 1. And now we have to just do a simple example to see what that all means. So, example, we go from, say, n plus 1 equals 3. We try to go back to n equals 2, to n equals 2. Okay, so this is what I have. I have an initial polygon with 4 control points, B0, B1, B2, and B3. And now I have to do this iteration given by the first formula. First formula, number 1. And I runs from where to where? I runs from 1 up to n, from 0 up to n, from 0 to 2. I is 0, 1, and 2. And something happens. I compute these bi bar values. The bi bar is b0 bar, b1 bar, and b2 bar. And these values are something. And so there's something here, something here, something there. And this is b0, b1, b2. And then it's minus something else, minus, minus, minus. And what goes there? Minus 1. So it is b minus 1 bar. Here it's b0 bar. And here it is b1 bar. Okay, now what are the ratios in front? Here it is always n plus 1. N plus 1 is 3, 3, 3, 3. And then here it is I. So it is 0, 1, 2. And we divide by what? N plus 1. N plus 1 is 3 minus 0 is 3. And then it goes down. 3, 2, 1. And then we divide by n plus 1 minus I, same thing. Divide by 3, 2, 1. So there's a pattern to it again, right? Okay. We only have to understand the geometry of this. What is the geometry of this? These are the points we're after. B0 bar, B1 bar, B2 bar. B0 bar is 1 times B0. That's it. Minus not 0 times something else. Okay, so B1 bar is B0. Which makes sense. Huh? We want to have that to lie here. So this guy is B0 bar. Okay, now we can construct B1 bar. B1 bar is a point on the line that is given by B1 and B0 bar. B1 is here. B0 bar is here. Okay, B0 bar and B1. So it's somewhere along this line. And I tell you where it is. It's here. It's exactly there. Why? Because now I have split this in a ratio 2 to 1, which we remember, right? This is the same rule. 2 units, 1 unit. So this will be B1 bar. B1 bar is a combination of B1 and B0. It has these strange numbers or weights in front of it. 3/2 and minus 1/2. And I come back to that later, what that means. Okay, how I can see that this point lies there, and not in the interior of the segment, but outside. Where does it come from? The last one is B2 bar. B2 bar is on the line given by B2 and B1 bar. Here is B2, and here is B1 bar. So it is somewhere along this line. And I tell you where it is. Here is the line. And again, this line will be split in the ratio 1 to 2. And here is that point. And that point is called B2 bar. Now this one does not coincide with the last one there. What happened? I started with B0, B1, B2, B3. And I constructed B0 bar, B1 bar, and B2 bar. So the original curve looked like this. That curve. And the curve that is given by the triangle polygon looks like this. Huh? So initially, they are the same, and then they diverge from each other and part. So very briefly, what does this mean? So this is just a note. Here I write a point is a combination of 2 other points with some weights in front of it. Okay. So I just say combination of points here. Combination of points. What type of a combination is this? So if I have 2 points, point 1 and point 2, and I give these guys names, and I call it point 0 and point 1, then these points define a line, right? So there's a line. This line is infinite, and this is a finite chunk, a line segment on that line. Now, I can write any point on this line. Any point on this line is a combination of weight 0 times the first point, P0, plus weight 1 times point 1, P1. Okay. So for example, this point P0 is how much times P0 plus how much times P1. P0 is 1 times P0 plus 0 times P1, right? So for example, e.g., you say P0 is 1 times P0 plus 0 times P1. Okay? Or you can say P1 is 0 times P0 plus 1 times P1. So these numbers, these weights, are called the barycentric coordinates of a point. So this point has coordinates, P0 has coordinates 1, 0, because it is 1 times P0 plus 0 times P1. This point has barycentric coordinates 0, 1, because it is 0 times P0 plus 1 times P1. Or the midpoint. What are the coordinates of the midpoint in this way? The midpoint is, following intuition, 0.5, 0.5, right? It's 1/2 times the first point, P0, plus 1/2 times the second point, P1. Okay. Now here I was dealing with points that were beyond the line segment, right? How do I get that? So for example, I can draw this point. Okay, that point. This point has coordinates too. The way I've drawn it looks like this is one unit, and this is another unit, right? Okay. That point has coordinates too, with respect to P0 and P1. What are the coordinates of this point? You see a linear progression here of the numbers of these weights. 1, 1/2, 0, or you see 1, 0. What is the linear progression there? 1, 0. Yeah, intuition is right. It's -1. Okay, what is the progression of this sequence? 0, 1, 2. Huh? Okay, interesting. That point has coordinates -1, 2. So this point is -1 times P0 plus 2 times P1. Okay, that's the way it is. Or look at this guy. What are the coordinates of that guy? So look at the progression. 0, 1, anyone? 0, 1, 2, has to be 2. And then the second coordinate is 1, 0, -1. Okay. Okay, so this point is 2 times P0 minus 1 times P1. Okay, so these are just called barycentric coordinates, this concept. Barycentric coordinates. And using this concept, you can also interpret these combinations, okay? Because you always have a point is a combination of two other points with certain weights in front of them. And the interesting thing is that these weights always sum to 1. When you sum these, 2 minus 1 gives 1. 1 plus 0 is 1. 1/2 plus 1/2 is 1. 0 plus 1 is 1. -1 plus 2 is 1. Okay? These weights always sum to 1. That is a result of having these new points lie on the line given by the 2 points. Okay? So this was just a little comment on that. So this was equation 1. Now we also have to follow equation 2 to do the same construction, right? Or a different construction. So now we do equation 2 and construct something. again we start with a polygon, B0, B1, B2, B3. And this time we start from the right end and extrapolate to the left. And we start I equals n plus 1. N plus 1 in this example is 3, so we go from 3 down to 1. So following equation 2, we use I from 3 down to 1. From 3 to 1. What do we get? So we solve for the bi minus 1 bars. Bi minus 1 bar, so this is b2 bar, b1 bar, and b0 bar is something. What is it? There are these ratios again, times b3, b2, and b1, and then minus something, minus certain ratios times b I starts at 3 bar, b2 bar, and b1 bar. And what is in front? In front is n plus 1, that is 3. 3, 3. And we divide by I, so we divide by 3, 2, and 1. And then it's minus. We divide by I is divided by 3, divide by 2, divide by 1. And then it's n plus 1 minus I. N plus 1 is 3, so it's 3, so this is 0, this is 1, and this is 2. Okay, so what does this mean? These are different expressions for the bi bar points. So what do we have? We have b2 bar equals b3. So this is b2 bar. The other point then is b1 bar. It lies on the line given by b2 bar and b2. And I tell you where it lies. It lies here, right there. This is b1 bar. Why? Because again, this is now split in a ratio 1 to 2. And the last one is b0 bar, and it lies on the line of b1 bar and b1. So it has to lie here. And here is that triangle, and I call it b0 bar. So what happened here? We started with this cubic curve, the original one, and then the new quadratic curve looks like this. So again, the curves are diverging from each other. But this time they are diverging as I move to the left. And here, the curves were diverging as I move to the right. Now what? And there is no good or unique answer to the now what question. When you have two answers and you have to combine the answers in some meaningful way, what do you do? On a high level, or just say on a summary level, what did I just do? That's the geometry. And the case was from n plus 1 equals 3 to n equals 2. I started with one polygon. And I constructed a new polygon for it. Let's see. It's not good. I want to do it like this. New triangle, and then pass through here, and new triangle. That's what I did there. And I had the results from formula 2, where I used the same polygon. and started the construction from the right end. And the result I get is this result. Okay. So you have a B0 bar, a B1 bar, and a B2 bar here. And you have another set of B0 bar, B1 bar, and B2 bar values here. Which is the answer? I have two answers for the same problem. Which is the answer? Right? I constructed one curve that looks like this, and I constructed the other curve that looks like that. Neither of the curves coincide with the original cubic curve, but they cannot, right? They cannot. So if I have an answer 1 and an answer 2, and both are kind of good, at least this one is good in this region, and this one is good in that region, then what can I do? You can average them, right? So you just say, okay, I have a bunch of control points here, B0 bar, B1 bar, B2 bar. I have a bunch of control points here, B0 bar, B1 bar, B2 bar. The final set is I just sum them up, divide by 2. Okay? So therefore, I just give these guys names double bar, okay? And I just say average the result, okay, average. So the average then would be BI hat is 1/2 of the BI bars plus the BI double bars. Okay, and you do that for I from 0 to n. The first one is more accurate at the beginning, and the second one is more accurate at the other end, right? So you could also have weights, how you average them, right? You may want to force them to preserve the behavior at the two ends, and in the middle have the error. That is already thinking ahead. Very good, very good. So you do not have to do it exactly. You can weight this, right? Depending on whether you are in the middle of the curve or at the end of the curve. Very nice. But this is good enough. What will this give you? This probably will do something like this. You have a cubic curve, right? The original curve looks like this. And now you do this averaging business, and you get a new control polygon, which probably will look somewhat like this. Okay, this is your new average polygon, and the original curve will be approximated by something. It looks like that. Is that a good way to average? No, it is one way to average. There is no best way to average. Okay. Does this make sense to everyone, what we're after? Why might it be a good idea in general to go from many control points to less control points? Why is this good? Where might this come up? Pardon? Faster, right? If you know this, right? This says this de Castillo algorithm. If you program it with this double loop, it's n squared time, right? So smaller n, smaller time. That's good. And the other thing is to do with compatibility or standard. If your software system only allows you to represent curves up to n equals 10, but a user clicks 50 points, then you have to go from the 50 points in the control polygon down to, well, the maximum supported by your system is 10, right? So what is the best 10? How do you go from 50 to 10? I only talked how to go from 3 to 2. How do you go from 50 to 10? You cut over and over, right? You go from 50 to 49 to 48, right? You cannot go directly from 50 to 10, or can you? Think about it, right? Maybe you can go directly from 50 to 10. It's a research question. But anyway, you want to believe me that sometimes a system will allow you only to deal with certain degrees, right? I think BMWs only allow you to go up to degree 17 curve. I don't know why that is, okay, but I think that's 17 or 18 is the highest degree that the BMW CAD-CAM system used to support. And maybe now they support everything. Also, the higher the n, the larger the numerical error. You will accumulate more and more error, right? But you know that because higher degree, more multiplications, no matter what. So far so good. Now comes a topic that relates to a different way to represent these Bezier curves, and it's based on this notion of barycentric coordinates, which I just talked about. So I need to talk about barycentric coordinates. Centric coordinates. What are they? In 2D, if I give you 2 points, point 0 and a point 1, then I can write any point on that line given by those 2 points as a combination of those. I just have this on the board, right? I can write any point, P, on that line as a combination of weight 0, P0, plus weight 1 times P1. Okay? And I also have a requirement that these weights sum to 1. That's the end. Weight 0 plus weight 1 equals to 1. Okay? So then this represents a linear combination of 2 points. And since it's linear, the result point P will be a point on the line, period. Okay? Now, further, one says this is a convex combination if the weights are also both greater or equal 0. If omega, if weights 0 and weight 1 both greater or equal 0, then this is a convex combination, and it would only define points on the line segments. Okay? A convex combination. Convex combination. And the other thing is this tuple, weight 0, weight 1, this tuple or this vector is the barycentric coordinate vector, or just the barycentric coordinates of P. That's what these coordinates or these numbers are called. So these are the barycentric coordinates, of P. Now I can do the same thing for 3 points. Okay? From 2 points, I can represent each point on the line. Now I take 3 points, and they define a happy triangle. Okay, point 0, point 1, and point 2. Now I can represent any point in the triangle, for example, as a combination of 3 points. Weight 0 times point 0, plus weight 1 times point 1, plus weight 2 times point 2. Okay, why does this make sense? So then there's a triple, right? Weight 0, weight 1, and weight 2 is a barycentric coordinate triple of a point. Barycentric coordinates, centric coordinates of P. Okay. Now help me to understand this. What are the barycentric coordinates of, this is P0, this is P1, and this is P2. So what are the barycentric coordinates of P0, of P1, and P2? P0 has coordinates 1, 0, 0. Just follow your intuition. P0 is 1 times P0, 0 times P1, and 0 times P2. Right? So what is P1? P1 has what coordinates? 0, 1, 0, 0, 1, 0. And P2 has coordinates 0, 0, 1, right? 0, 0, 1. Okay, now I give you a midpoint. I give you this just an example so you become more fluent with this. I take the midpoint of the line segment between P0 and P2. So what does that point have in terms of coordinates? That point is the midpoint of P0 and P2, so follow your intuition. It has coordinates 1 half, 0, 1 half, 1 half, 1 half, 0, 1 half. Okay. Now what the center of the triangle, the centroid of the triangle, is the average of the three corners, right? So that is 1/3, 1/3, 1/3. Right? This is the centroid. Centroid would be another example of a point with coordinates 1/3, 1/3, 1/3. And again, you see that all these coordinates sum up to 1. Huh? They sum up to 1. They sum to 1, they sum to 1, they sum to 1. And weight 0 plus weight 1 plus weight 2 is 1. That will just mean that any point you construct lies in the plane of that triangle, because this triangle does not necessarily have to lie in the board. This triangle can also lie in space, right? So this is just notation. But then if I introduce this notation, I probably do that for a purpose, right? Notation. Why do I do this? Why do I do that? There's a standard notation for a Bezier curve, and there's a barycentric notation for the Bezier curve. And this barycentric notation of the Bezier curve will become important later on when we talk about patches. Okay? So right now, you think of Bezier curves as I take a piece of line and I deform it into a curve. When I think about curve surfaces in space, what is the analog of that? Here I take a piece of chalk, straight, and I deform it. What is the most primitive surface element I can do that with in space? I take it, what type of, and here I take a line segment. And if I want to shape something in space, a surface, then what is the simplest one? A triangle, right? So this is in XY space, right? And then now I do something in XYZ space, XYZ, and the simplest patch I can construct in 3D is a patch that is bounded by 3 boundary curves, right? A triangle. And so then I need to worry about taking a triangle and morphing it or deforming it into a curved triangle. That triangle and then bending it. Here, straight line, bending it. So for this, we need the notion of barycentric coordinates. So it will become important in that context. So that's why I talk about it now. So you can also write curves in this barycentric form. And so this doesn't really introduce any new concepts. It only introduces a different representation for the same thing, namely the Bezier curve. And the book introduces it at some point. So I will just split this, and I will just say standard representation, and then the barycentric representation, barycentric representation. Okay. So the standard representation is this. I have a polygon, I have circles, I I give these circles names, B0, B1, B2, B3. And when I evaluate, I put these points into a scheme, B0, B1, B2, B3, B0, B1, B2, B3, no B3, B0, B1, and B0. And now I give them generation indices, so this is generation 0, originals, 0, 0, 0, 0, first generation, second generation, and third generation. And there is a line, which I call the T-line, and I evaluate for some value here between 0 and 1. When I do that, I introduce the intermediate points, giving intermediate polygons, and those have names too, and that was B01, B11, B21, and this was B02, B12, and this is the point on the curve, B03. And the points are also in the scheme. And there was a particular key that you use to construct one next point from the two previous points. And so the key was a particular value, Bij, was related to the previous point by saying 1 minus t times B I, j minus 1, plus t times Bi plus 1, j minus 1. That was the key. This is what we know. And now there is a barycentric version of that, which just uses a different indexing scheme, essentially. So the barycentric version of that looks like this. The geometry is all the same, but it calls these points differently. So the first control point is called B30. The next one is called B21. The next one is called B12. And the last one is called B03. What do you see when you look at those indices? 3, 0, 1, 2, 2, 1, 0, 3. What happens? It's the way you can sum integers into 3, right? Okay, that has to do with this degree, right? It's a degree 3 curve. That's how you can 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. Yeah? So, and there's probably the scheme. The scheme looks the same, right? So there's B30, B21, B12, and B03. Okay, now we take these and construct new ones from them. B, B, B. Follow your intuition. In the first column, we have to sum to 3. In the next column, we have to sum to 2. Okay, so how can I decompose 2? 2, 0, 1, 1, 0, 2. Next column, the numbers have to sum to, follow your intuition, 3, 2, 1. So it is 1, 0, 0, 1, and the last one has to be B, 0, 0. Now the generation index, this is generation index 0, 0, 0, 0, generation index 1, 1, 1, 2, 2, and 3. So this is generation 0, 0, and 0, and okay, I'm not quite sure about the line yet, but I put the points here. These are the same points as previously, but they have different names. So the names for these guys are now B2, 01, B1, 1, B 0,21. This point is B 1,02. This point is B 0, 2, and this point is B 003. Interesting indexing scheme, right? Much more complicated, but elegant in a sense. We will see that it's elegant when we come to the triangle patch. And again, we only have to understand how we combine elements in the scheme to obtain the next element in this triangle, in this triangular setup. So we have to understand how this guy is related on that. And so here we have a b I comma j of generation k is something times this point plus something times that point. If this is ij, then this is I plus 1j, right? So it is something times b I plus 1 j of generation k minus 1 plus b, if this is ij, 1, 1, then 1, 2 is ij plus 1, bi j plus 1 of generation k minus 1 times something in front. And now I put the values here, and the values are u and v. Where do they come from? We express everything in terms of two parameters, u and v, on this line. This is 1, this is 1, and this is a line, u plus v equals 1. And we move in that direction. Here we moved in that direction on the t line. This is bizarre, right? I mean, talk u and v and so forth, but it's really, I see u and v, here is u plus v equals 1. So u is 1 minus v, right? So I could say this is 1 minus v times something plus v times something. Then it's very similar to the other form, right? U and v are not really the two different independent parameters. They are coupled by this equation, u plus v equals 1. So if you solve it for u, you get u equals 1 minus v, and you really have 1 minus v times something plus v times something else, which is the same thing on the other side using t. Okay. Why? There is the so-called multi-index notation. And so the standard is this guy. A curve depends on t, which is the deformed version, I from 0 to n, of control points bi times bi n of t. And t runs between 0 and 1. That's what we now know. And now the barycentric form expresses this c of t dependency using two parameters. Namely, c depends on two parameters, u and v, equals sum I plus j equals n, and I comma j greater equals 0. And now comes this multi-index notation, bi comma j times n factorial over I factorial times j factorial times u to the i's power and v to the jth power. Okay. Now I can summarize this. This is sum I plus j equals n, I comma j greater equals 0. And I say this is bi comma j. And these expressions are called Bernstein polynomials in a more generalized sense. These become my Bernstein polynomials bi comma j of n. And they are dependent on two variables, u and v. So these are the generalized multi-indexed Bernstein polynomials, bij n of uv. Okay, and now I can compactify that further and just say sum. And now I use a multi-index, b sub a boldface index I times b sub I, a boldface index n of u, and u is a parameter, uv. And I can say this is I multi-index equals n. Okay, so this is a very compact form for writing that. And you are fooled to believe that now everything depends on two parameters, u and v. But that's not really true because they are coupled. Where, and this coupling is expressed here, where u plus v equals 1 and u comma v greater or equal 0. Again, I only put this on the board so when you come into the section in the book where Gerald Farron talks about this other notation, you have somewhat a feeling where it comes from. Okay, it's the same geometry expressed using a different representation. And the purpose is to prepare for triangle patches in space. Okay, then this notation becomes more elegant and more appropriate. Is anything confusing about this or awkward? I know it looks awkward, but when you think about it, it's all about pattern, right? It's always just about pattern. That's why I can memorize this stuff, right? In fact, I do not memorize anything. I just remember the patterns, right? This is all about pattern. And if you can make this figure, all the rest follows from that figure. And you look at this and you see how this ij and this k is changing in that scheme that is reflected in the geometry and that is in that formula. And this formula is a double loop, right? Make sense? Okay. Again, there's no homework assignment is related to this. I just want to put this on the board so when you see that in the book, you have heard it before. Okay. And this becomes relevant not before we start talking about patches, triangle patches in 3D space. All right. Barycentric parameters, barycentric coordinates. Interesting stuff, isn't it? Now let's see on what note I should conclude today. This is actually it for today, so I can do an outlook. Next time, I will start one of the most important topics in all of geometric modeling, that's interpolation. Okay. Next time, I will start talking about this, interpolation. What is interpolation? Help me.
It's like extrapolating between the points.
You have points? You give me points, right? You say you give me points? You give me these points, right? Okay, now what do?
You estimate what data would be outside the points or in the area that does not equal a point.
Okay.
It's hard to describe.
It's hard to describe.
Yes.
I give you 5 points, and I want to find a curve that passes through these five points. Is that interpolation? I give you 5 points, and an interpolating curve is a curve that passes through these 5 points. That's interpolation. Okay? I give you 5 points, and an interpolating curve passes through those 5 points. So what is the simplest curve that I can construct? Which you have implicitly in the back of your mind anyway when you do click, 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 click. So the simplest curve is, of course, this one, right? The polygon that's given by the sequence of points, right? It's the simplest interpolating curve. Is this the one that you want when you do click, click, click? Maybe, maybe not. Maybe you want this curve, right? This is also a curve that's allowable. No? Yes. I said I give you 5 points. I give you a curve that passes through those 5 points. That curve is doing that. No? Okay. Okay, I can also give you this, right? This is also an answer. Another one. That curve does it too. Right? It passes multiple times through the given points. That's an answer. But what is the best answer to solve the problem? Depends on you, right? What you define as good, and then among all the good solutions, the one best. But maybe you want this, right? Something like that, right? That's good, really good. Why is it good? Why is that good? It looks smooth, right? So it is best, it's optimal in some sense. When you talk about an optimum, it is an extremum of something, right? Of some function, of some cost function. Nature always optimizes something, right? Right? So if you do a physical experiment and you take a deformable plastic fiber-like material, and you have a bunch of little these are like screws maybe, right? And you can put a little direction in there. And you were to put some kind of deformable material there, right? Like a deformable plastic-like ruler that you can deform without breaking. Then that ruler, this little piece of wood, maybe even wood, certain types of wood, right? You put wood in there, one piece of wood would bend and deform in a certain way. And the way it would bend, well, it would bend like this. Right? It's the natural way the shape would evolve when you force a piece of deformable material through these screws, right? They would orient themselves like this. Now, there is something that is called a cubic spline. And it does something that nature does. Nature minimizes the internal bending energy that is stored in this bent material. Okay, so the cubic spline is also called the natural spline, right? Because nature takes on this shape, natural spline, and it minimizes the internal energy. Minimizes. A form of energy, of a curve, Okay. Another interpolating curve would be this one, right? But you don't like that one either, right? So this is what I talk about next time. And the first part is just talking about this. I give you a line, I give you a bunch of sticks, and then we want to construct the curve that passes through those sticks. And if we understand that, then we can also do this, right? I give you a bunch of points, and I want to do that, right? This is more general than that. And that's what I talk about next time.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.